Now, there are many ways to make the circuits for these, but before we make the circuit, let's make this problem more complex, because how often do I just do this? Not often, because I normally have more than one column of things to add, right? And when I'm in the middle of a problem, I have to take that carry bit and put it on the top, right? So this is actually called a half adder. Because it's actually not solving the whole problem. Because the whole problem that I could solve for all the columns of addition is if I had 3 inputs, and one of them is a carry from a prior addition. Right? So if I went one column over, I could put the carry in here, and then I could have some digits in the second column. And then if I had an adder that would do 3 numbers as inputs, then that would solve, I could do the entire adder for however many digits I wanted by stringing them together. Okay, so let's do a full adder. So a full adder has to have a carry. It has a digit, and it has 2 digits to add. We have to have a carry out, and we have to have a sum digit. So we make our truth table like we normally do. And then all we have to do is figure out what the sum digits, sum and carry digits are. Very easy when everything's zeros. And addition has a property that's either associative or commutative. Which is it? It has both, right? Associative means it doesn't, if I want to do 3 things, it doesn't matter which pair I do first. And commutative means it doesn't matter which order. So if I'm going to add these, I can just look across and say, oh, there's just one 1, so that is 1 carry a 0. There's just one 1, that's 1 carry a 0. There's 2 1s, so that's 2, which is 0 carry a 1. So when you're working these problems, you want to do it in a way that makes sense for you. And I'm going to do one more thing, and then I'll answer your question. So I could have actually put the decimal output here. This is the truth table, and I'm using it for my own good. Sorry, talking and writing at the same time is not working today. I'm hearing some corrections, but the 4th row? Oh, okay. That should be a 2. The 4th row should be a 2. Okay, good. Thank you for catching that. So I could have written a decimal. And that would also just help me do my truth table faster, right? So I can write whatever I want in my truth table because it's a shorthand for me to write down things that are true in each row. So you can write that. It's totally legal to do that. You had a question? Yes, I have to add up all 3 digits, right? When I do regular addition and I have a carry bit, a carry something from the previous number, I have to add it, just like all the other numbers. Let's do it. When I add these numbers, I get 11. 1, carry the 1. You add the 1 with the 5 and the 9, I get 15. Carry the 1. Yes? Regular addition? Okay. So we always add the carry. Like, we don't care that it's a carry. We just add it. Same thing with binary. It works the exact same way. Does that answer your question? Okay, so now we need to make circuits for these. So let's look back at our half adder. Our half adder, these two columns look exactly the same as the first half of this table. Right? So we could use something from there. So actually, basically, we're ignoring carry 0. Well, that makes sense because the carry 0 is 0. So it does look like a half adder in the first half of the table. In the second half of the table, can you see anything from S that look compared to the first half? It's the opposite, right? So whenever we're doing circuit reduction, like we can just, in order to make a circuit, I can do disjunctive normal form and I'll be guaranteed to get a circuit that's going to work. But I can also be clever and look at parts of my table and use things I know about them to make a simpler circuit. Does anybody know what function that is? That's exclusive OR, right? This is the opposite of exclusive OR. This is an OR, right? And this is an AND. So let's use our human intuition and logic to actually write the circuit for this. But you should practice writing it in disjunctive normal form and drawing a circuit for it just for your own practice for the test, because you're going to have a problem like this where you might not see a pattern like this, so you need to practice writing things in DNF and writing circuits for them. But we're going to be clever. So to make C1, this is clearly an AND of two variables. Which two variables? So that's going to be an AND of X and Y, and in the first half of the table we also have what? We have not C0. So we have to put that in there to make sure that we're only dealing with the first half of the table. On the second half of the table, we have C0 being true, and we know that we're going to OR two things together, and it's going to be X0 and Y0, because if you look at this part of the table, that's exactly like the truth table just for X and Y together, right? So if we look at the bottom half, it's like a repeat of the top half. So I can make any truth table by taking the smaller one and putting zeros in front of it, and then replicating the truth table and putting ones in front of that. That's actually what we do. So this is C0 times the quantity X0 plus Y0. And then I can just OR these two things together. If I OR them together, why is that okay? If I didn't put this on there, I couldn't do it, right? So the reason why I can do it is because not C0 is only true in the first half, right? So this function is going to be zeros in the second half. Does everybody see that? This function, C0, is going to be 0 in the first half, so it'll have all zeros as the output. So I can OR these two things together and not ruin any of my outputs. That's why breaking your table into pieces according to when one of your variables is 0 or 1 is a great way to deal with it. And you always want to do the leftmost variable for that, because that's the one where you can easily see where the split is. So if you have an intuition that one of your variables is going to split your world in half, then put that one on the left, and it'll be easiest to find the pattern with that. Okay, so this is our equation for C1. Is that reduced? Most likely. I probably cannot get any better than this. Because there's nothing in common to factor out between these, except for maybe a Y0. I doubt it'll get less complex if we do anything with it. Okay? So let's do the same thing for S. Okay? In the first half, we decided that that looked like exclusive OR, and we know that we're just talking about the last two variables. It wasn't an exclusive OR, but now it is. Okay? And the second half is going to be the same thing but negated. So the output of the exclusive OR negated, and then we can OR those two things together. Any questions? Am I going to let you draw a circuit with an exclusive OR in it? No. We need to write what exclusive OR is with ANDs and ORs. Okay, so we've got a nice circuit here, but we need to actually compute the exclusive OR with a circuit using ANDs and ORs. So let's figure out how to do that. So this is S1. Any questions about how we got that? Okay, so the first thing we're going to do is make a circuit for exclusive OR. Okay, so the definition of exclusive OR says X or Y, but not both. So I can literally write my equation from that. X plus Y, but actually means and, not both. So let's draw a circuit for that. So there's the not XY. Now I'm going to do something that's kind of cheap, but you're allowed to do it. That is now my exclusive OR circuit, and now I'm going to reuse it. So if I tell you you have to draw something with ANDs and ORs, you can draw it and then use that new circuit that you've drawn. Because that's actually what we do. As engineers, if we're going to make a circuit, we figure out one piece, and then we never draw it again, because we might make a mistake if we draw it again. Okay, we refer back. Look at this diagram for this thing, and now I'm going to use it whenever I want. And by the way, I'm going to draw it like this. Right? This is the same as in logic. You can make up your own axioms and then name them and use them. So if I tell you you have to use ANDs and ORs, we'll do part of it, and then you can make your own gate and use it again. So let's do that. For S, so we had S1 was equal to not C0. So in order to do this, I need to exclusive OR X0 and Y0 together. And I need to AND that with not C0. And I also need to negate it and AND it with C0. And then I OR those two things together to get S. Is this the only way to draw this circuit? No, it is not. You could also calculate the exclusive OR twice. You could have drawn it with the ANDs and OR gates. There are many, many different ways to draw this. On homework 2, the last question, I know you don't read instructions, so I'm going to tell you what the instructions are so you can forget this also. There's actually a link to a little program called Circuit Builder that will allow you to build circuits, and it will give you the truth table output for it. So I linked that just so you can play with an online tool for dragging around gates and having it make circuits for you. So if you want practice with that, you can use that tool to actually make some circuits and see what the truth tables are and vice versa. So occasionally you should look at the directions and try them out or see if there's cool links in them. You're not required to use that. If you probably can easily figure out the truth table without doing it. So the instructions say to go use a circuit builder. You don't have to. It was just so I can link to something cool for you. If the link is broken, please do let me know, and I'll find something else to link for you. Okay, so now we need to make one for C1. And I'd like you to try that and then check it with your neighbor. All right, let's draw this. Now, if this is something new for you, then it really is as easy as it is. So you shouldn't ever sit and look at your paper and go, I don't know what to do. This is an AND of three things. So I draw an AND gate, and I put those three things on there. So it's just as easy as that. So if you don't know where to start, just start with something you can. Okay, and then this is an OR. I can't do this until I have this OR done. And I can't do this OR until I have this term done. So, like if I try to do something, I'm not going to be able to do it unless it's the right thing. So I can do this OR of x0 and y0. And then I need to AND the output of that with C0. And then these two terms are finished, so now I can OR them together. And by the way, don't connect these lines because they have different values on them. So now this output would now give me C1. Any questions about that? Now, what happens after we make circuits like this is we've reduced it, we've made the circuit with ANDs and ORs, then someone figures out how to make it really tiny and produce a chip for it, and then they reuse it over and over again within a computer. And what they do is after we have a chip for it, we think of it as a black box. So we made our circuit for our exclusive OR, and then now we just use the shorthand for it. So by the way, this isn't two separate gates. It's just an exclusive OR. So I drew it kind of messy. So it usually looks like this, and it just has an extra line on the back. So that is the gate. So that's the picture for what exclusive OR looks like whenever we refer to it. What it does on the inside is this. So when I drew a box, that's basically what we do when we draw a box, but we usually don't have the inputs repeated. So what we'll do when we draw a box around something is that if I've repeated the inputs somewhere, I'll actually connect them all up to those inputs. So I only have to put them once into the box. So let's redraw that, how I would do it. I would actually draw the box out here, and then I would have one X and one Y input, and I would connect this X up to here. So I'd probably do my nice lines like you guys do. And connect that in there, and connect my Y over here. Okay. Yeah, we just squiggle around. Okay, it's very ugly, I know. Okay, so that's because I was drawing on an existing piece of paper. All right, but now this is my black box. I don't care. Once I figured this out on the inside, I don't care how it works. So now I can treat an exclusive OR as something that just gives me the output I want with X and Y as input and exclusive OR Y as an output, and that's why we can draw this little symbol and use it. And in reality, somebody has done even something more basic than that to build AND and OR gates, right? So we're not even going to talk about how they work. Maybe you'll take a logic course that will tell you how they work. But we're not going to do it. So there's something on the inside. And what is that? That's abstraction. Okay, what we're doing is abstraction. So once we figured out how to do something, we don't do it again. We give it a name, and we call that, now we work at that level. So we work at different levels of abstraction. That's a really core computer science concept, and so we're kind of using it over and over again. So if I say, well, now I'm going to call this variable this, I'm making another layer of abstraction. So how would I put my adders together in a circuit? So what I would do is, for my sum, I'm going to draw a box around this. And my S bit is going to have these things inside. And to get not C0, I only want to put C0 in here once. So I'm going to have to actually put an inverter in there. Okay, so that's what I would end up with for my S. And in reality, when we build an adder circuit, we're actually going to put both of these circuits on the chip and have two outputs. So I draw a box around this one too, but I don't have any room to even make a messy input and output thing there. So basically what I'm going to end up with, though, is a box. Okay, so I'll have C0 and X0 and Y0 as inputs and C1 and S1 as outputs. And then if I want to add several columns of things, I need to hook them up together.